things work. So, go ahead.
Awesome.
You have the right lighting?
Yes, I think, can people hear me?
Yes.
Yeah. So let me echo your teacher's request. Not only should you ask questions, I'll be slightly sad if you don't, because it means that you guys are not super engaged with the material. Yeah, so as Hossein explained, kind of our goal for today is kind of to open a little bit the curtains and let you in on kind of like the kind of stuff that we like thinking about. We've been thinking about this for a long time. I made the joke that we're about twice as old as you guys, so it will be hard for us to remember exactly how it was to be a high schooler, so please stop us if we're going too fast, or even if we're going too slow. So, but the point of this is to kind of like excite you guys about science and excite you guys about the quantum world, and so please let us know how we can make that mission better. And today what I want to tell you a little bit is about how kind of like our views of what light is have changed, and how kind of like that shaped our understanding of the universe. And kind of maybe addressing your question, you could think of quantum as kind of like a paradigm shift between what we understood the laws of nature were in the time of Newton into something more modern. And I'll kind of allude to a little bit of that. And each of us is going to effectively talk about different facets. We're not here to necessarily give you a lecture so that you can go out and do quantum. We want you to be excited about it so that maybe when you go to college or when you go back home today, you look things up and maybe even shoot us an email and ask questions. So that's kind of like what we're hoping for. Yeah. So why are we here? I think it's important to acknowledge that this year is the year of quantum. It's kind of like, I think it's an initiative that's been put forth and has kind of Hossein explained, and I kind of bury the lead here. One of the reasons why we're celebrating this particular year is that it's been about a century since kind of like the development of our modern understanding of quantum mechanics. That was in 1925, and it was kind of by Heisenberg and Schrödinger that came with different perspectives onto kind of like how the fundamental laws of the universe were different. But our goal for today is not necessarily to focus only on this, to celebrate this, but it's not just to focus on this century, but kind of take a broader perspective on kind of what led to us realizing that something was missing, and kind of like what were the ideas and the concepts that we figured out, and kind of like the coolness that you get once you think deeply about what seem to be very innocuous questions. So I'll kind of give an outline of like our talks with some pictures. So I'll start by mainly focusing on light and telling you about some esoteric things like the photoelectric effect and how Einstein was related to that, but also how that led to the invention of the laser pointer that I should use instead of pointing at things. And there we go. It even matches the color. Ruben is then going to go on the other side and then tell us a little bit of how quantum mechanics gives us a different understanding of how matter works. What makes, for example, atoms stable, how we can actually get light speckle patterns of matter in a way that we only think that we can get when we have waves. Oriane is going to take us from a single particle to many particles and telling us what happens when we have basically the correlated dance of many elements and the kind of cool new phases of matter that we can get, and kind of that we'll end up with seeing some stuff levitating today. Christian is going to focus how these new laws kind of give us a new perspective on how information is encoded in a physical system, and how we can use that for doing interesting things, for example, security, but even computation. And as kind of Hossein alluded to, at the end we'll have Tommaso and Alyssa who will tell us a little bit how some of these ideas are going away from kind of like just the academic laboratories, and now we're thinking of how to build machines that kind of allow us to kind of probe these weird features of quantum mechanics to do some interesting physics. So hopefully that kind of gets you super excited. And I realize that this is a busy plot, but hopefully it's also a very exciting plot, and we'll thread that needle quite well. Yeah. So as Hossein said, classical mechanics tends to explain the world very well. If you were someone in the 1900s and you had access to an AI-generated image of the 1900s, this is what you'd see. And you'd be quite happy with the state of physics at that point. You'd look at this landscape and you'd be like, oh yeah. Oh, yeah. Oh, I didn't get this. I know how mechanics works. I know F equals ma, so I know, for example, how the train moves. I know gravity, so I know how the comet moves. I know, basically, I can predict all of these aspects. I also know electromagnetism. So even though I have some telegraph lines, I know why signals propagate through wires, and I can understand why there's kind of like light coming out of the castle. And you also would have thermodynamics. So you knew, for example, how heat exchanged between the atmosphere and the lake. You kind of have a broad perspective that animals are kind of like thermodynamic engines. And you could think of yourself that basically physics was done. And that was kind of like actually a little bit the perspective then. But there was this guy that had this kind of Friday evening lecture, which is always a good time to spend your Friday evenings. And already in the 1900s, he kind of alluded to the presence of kind of two small clouds on this kind of idyllic AI-generated landscape. And one was a very subtle question, which is what light is emitted by a hot object? And the second one was, what's the motion of light through ether? And these are very esoterical, kind of like almost nitpicky like questions that you get like sometime when someone's being very annoying and they want to ask too many whys. But the kind of like amazingly prescient thing about this lecture is that these two questions fundamentally changed what led to the discovery of all of modern physics. For example, understanding how light moves and this notion of whether or not there is an ether is what led us to understanding general relativity, understand this notion of space-time, predict black holes. That changes our perspective of kind of cosmology. And this other very innocuous question is what led to what we're talking about today. Very much like it motivated a lot of the developments of quantum mechanics and what it means for, and I'll explain exactly the origin of this word of quantum. So as a good introduction, I introduce it very broadly, and then I decide to discard all of this bottom corner, so I'll just focus on this side. But I want to focus exactly how this particular simple question and kind of the ideas that it encodes change fundamentally the way we understand light, and as a result, how we understand the universe. So quiz time. So these are kind of bars of metal that come out of like a forge. Which one is hotter? Okay, good. Okay, that's 1 out of 1. Everyone's getting 100% so far. And the question is why? Do people have an intuition? No wrong answers. Anyone wants to?
Come on, someone take a guess.
Oh?
Be bold.
Yes. So you can see it. So your point is like this is brighter. So it's like hotter. It's like has higher temperature, has more energy, so it shines brighter. That's a good answer. That's true. Why does the color change? Okay. So your point is that red is less energetic than yellow. So this is kind of like more energetic. Is that a fair translation of your point? Okay, maybe let me move to a different example. So it turns out that if you look at light, if you look at like constellations in the sky, and you carefully look at stars, you also notice something cool, which is stars are actually different colors. Like we think of the sun as being yellow, but turns out that that's a particularity of sun, and some stars are actually blue. So if I order them by color, I can ask the same question, which one is hotter? Okay, that is true. Okay, I need to ask tougher questions. I see you guys. And the question is, the motivating question that a lot of people were confused by is, why is that the case? Like, how do I predict? It seems like color is indeed a fingerprint of the temperature of an object. But as a physicist, I don't just want to know, like, if I move a little bit, I go in that direction. I want to quantitatively understand, if I give you a temperature, can you predict what color it is and what's, for example, the spectrum? And in particular, let me be a little bit more specific of the question that we're asking, you have some intensity of light as a function of the frequency of light. And the thing we didn't know at the time is exactly how to predict this. For example, what's the shape and which location of the spectrum this is. So it could be, maybe the spectrum looks like this for the M, maybe for the F it looks more or less like this, and maybe for B it's kind of like closer to this. We didn't know exactly how to go. And this was kind of like a very weird question, because if we understood mechanics, we understood how particles move, we understood electromagnetism, we should just be able to compute this in some way. And before going into the ideas for those, it's important to review a little bit what is light. So do you guys know what, have you guys taken electromagnetism? Okay.
So this is an E&M class.
Oh, perfect. Okay, so this is going to be a review. Okay. So you guys are very much aware that indeed, like, light is a wave. It's a combination of an oscillating electric field and an oscillating magnetic field, that the way they combine together gives them some propagation in one direction. And crucially, E&M, this kind of simple idea of a wave, explains this all the way from radio waves, the thing that you use in your car, all the way to X-rays, the thing that you use to see bones if you have an accident, which I've had when I was a kid, and something that you don't want to experience, which is gamma rays. And deep in the middle is this optical, this visible regime, and this is actually the lights that you see, which is actually only a very small parameter regime of the entire spectrum of light. And as you've noted, indeed, like red is the more low energy color, and then you go all the way to violet, and that's kind of the most high energy color, which always surprised me because we always assume red is like the warm color, but it turns out that the most energetic colors are in blue, which for me is always kind of, it always feels counterintuitive why that's the case. Sorry.
Could there be wavelengths that are like bigger than buildings, like as big as galaxies or something, that just have such low energy that you can't really like detect them, or like smaller wavelengths? Like, is there like a cap?
Yes.
Kind of.
No, technically it could be arbitrarily large and arbitrarily small. You can imagine that if the wavelength is so big, the frequency would also be very slow. So what you'd effectively see is basically a very slowly moving electric field or magnetic field. So then it depends. You need to measure for a very long time to be able to see that frequency. But good question. Any other questions? Okay. And the other thing I want to introduce to make sure we're all on the same page is exactly how light is generated. So you probably also had learned a little bit about this. Turns out that you don't need necessarily a point charge stationary. What you need to generate light is to basically get it in motion. And the motion of charged particles is the thing that kind of induces these oscillating electric and magnetic fields, and that allows you to propagate an electromagnetic wave in light. And so at the start of the 19th century, there were kind of like two different perspectives on how exactly the origin of light from an object came. One was to think of the thermodynamics of particles. You think of a star as kind of like a bunch of particles that are moving back and forth. And because they're moving and they have some charge associated with them, they would start emitting radiation. And this is kind of one perspective that gave us one particular prediction that it's not super clear the details. The only thing that is important to emphasize is that here it's kind of exponentially suppressed, and by effective that is kBt, and that's the thing that encodes the temperature part, in temperature dependence.
So when you say it, what is I representing in that?
Yeah, so very good question. So I, it should be the intensity of the light as a function of frequency nu for a given temperature T. So you should imagine that at very small frequency, this term is about 1, and you just have a nu to the cube. And then at large frequencies, this exponential should dominate, and you get a decay that's exponential. So it should be peaked around something that is about 1 over kBt. That was good? But there was a completely different perspective that thought of light very much as a wave effect. And if I will simplify the wave nature of light by thinking of guitar strings because it makes the plot much easier. And you could think of a star as kind of like a box. And inside that box, there's kind of like different modes of light that all could be excited. And one thing we know from like statistical mechanics is that in principle, if you can populate each mode with a particular amount of energy that's related to the temperature of the system. And if you do this, you have a completely different expectation, which was that now the intensity no longer had this exponential cutoff. It actually just increases with increasing frequency. Okay? And people went about and they did some measurements. But before this, which one do you think is correct? What?
Wean the exponential.
Why?
It doesn't make sense for something just to keep growing indefinitely.
That's very good intuition. It's always good, like if it blows up, you have infinite energy, so something has to go wrong. Turns out that people still propose it. But indeed, once you met, what happened is, indeed, if you think of just the thermodynamics of light, you get this blowing up, as you correctly pointed out, so that can't be the right answer. What you get is something indeed that is peaked, but the crucial thing that people notice is that it's actually not exactly the right result. So you see that the curve between the Wien prediction agrees with the true answer at very large frequencies, but it doesn't agree with it at small frequencies. So it's kind of, it was a good prediction, but it was not a perfect prediction. Turns out you can still, it turns out that the formula is slightly more complicated, and I'll get back to it. But the point I want to emphasize is that it was good enough that it won him a Nobel. So one thing that is important to note in science is that we'll never know the truth. Our goal is to get closer and closer to the truth. So we need to, the point I want to emphasize is that getting that there's no perfect answer. All that we do all day is basically trying to get a better answer. And that's always the motivating question. And so people look at this and they started looking, they had this prediction, they started looking at the difference. And the question was like, how do we extract the right curve? How do we actually understand this particular curve? That's neither light nor particles. And turns out, so we have two predictions, one going from the thermodynamics of particles, one going from the thermodynamics of light. And we want to get something that also has an exponential and some power laws. So quiz time, this is a harder question. Which one should be your starting point? Any guesses?
The particles?
That would be also my guess. But it turns out that the answer is that you should actually think of the thermodynamics of light, but with a little bit of a twist of how you think of the mode, putting energy into the different modes. So when we thought of the previous experiment of putting the energy on each mode of the guitar string, we implicitly were assuming that the energy of the guitar string is kind of proportional to how much we pluck it. If we pluck it a little bit more, we put a little bit more energy. If we pluck it only a little bit, we only put a little bit of energy. So there's kind of the energy that the guitar string can hold is actually a continuous variable of the amplitude. It turns out that the key insight for going from here to this particular formula is to assume that this is no longer true. And assume that instead we can only pluck the guitar string on certain amounts. So we can only pluck it maybe, well, we don't pluck it at all, and there's a little bit of energy there. We pluck it only by 1 unit, and we get 1 unit of energy, or by a factor of 2 or 3. But the crucial aspect is that this continuous spectrum now becomes discrete. Okay? And if we do this, what happens is that temperature eventually at some point will never, even though the temperature is hot, the system is hot and has a lot of energy, it'll never have enough energy to populate these modes. So this blow up that we saw before actually gets tamed down. And that's kind of the origin of this exponential suppression. It turns out that the guy who came up with this didn't really have a good reason why this was the case. He did some math and he figured out that if this was the case, you can actually have the right formula. And for that, he got a constant named after him, and he also got a Nobel named after him. So the point here is that often you don't need to have the full answer. don't need to have a full explanation. But again, it's all about trying to understand better what is happening in the world. Okay? So if this only explained how light is emitted from stars, it would be kind of boring. But it turns out that this simple idea of the energy coming in packets actually explained a completely different phenomenon. And this was known as a photoelectric effect. The photoelectric effect is kind of, it has photo, so it has light. It has electric, so it has to do with electricity. And it was actually something that was realized at the start of when people were playing with electromagnetic waves. That basically if you had some light and you shone it on kind of like two plates of metal, what would end up happening is that electrons would hop out of the metal and go into the other electrode. Okay? And this was kind of something that people didn't really understand. When people started doing these experiments, their trick was actually to cover everything with a sheet of cloth so that this stopped happening and they could do their experiments neatly. So a lot of people ignored the problem, but when they started looking at it, they saw something very confusing about this effect. What they were seeing is like, they were asking the question, if I vary the type of light that I use, how does that affect the energy of the electrons that are emitted? And in principle, what you'd expect is that, for example, if you put more light in, for example, if you crank up the intensity, the electrons would move faster. It turns out that was never the case. The only thing that they could move to affect the energy of the electrons was the frequency of light. And they saw this very weird effect where they saw that basically you had to be above a particular frequency, and then the energy of the electrons would be proportional to the frequency of light. And you had this kind of almost like weird behavior, right? Kind of like a turn on. And the puzzle is like, why is that the case? Why does it not depend on the amplitude of the light? And again, the idea, the puzzle was exactly that indeed light interacts with the electrons in these packets of energy. So it's not just about how much you can pluck these kind of proverbial guitar strings. Actually, when light comes from like a light bulb or a candle, it comes in little packets, and it basically kicks off an electron that again is able to move to the other side. And you have this simple idea, what you end up, and this is exactly what we now call a photon. And with this simple idea, you can actually explain this curve very simply, right? So you can imagine that when electrons are in the metal, they're in like a big box. And when light comes in, if it's at very low energies, low frequencies, it tries to kick out an electron, but it just doesn't get out of the box. It goes back down. If you put a little bit of energy, it spits out, and it spits out with some energy. And if you do higher frequency, higher energy, they spit out with additional energy. And this gives you exactly this particular curve. But this is kind of like an interesting note. But the quantitative prediction that this theory would make is that the slope of this is exactly the Planck constant that we introduced before. So building on the other idea, what this effectively gives us is kind of a perspective for solving an entirely different problem. That's the importance of science, is not when you try to find an answer to solve the problem that you're looking for, is when the answer that you find explains other problems as well. And crucially, there was like a falsifiable statement that you could make. If this theory is correct, the slope of this has to be the Planck constant that is related to the light of stars. And indeed, that was true. And this also got this guy a Nobel. Turns out that it got Einstein a Nobel. So even though he's famous for all other things, this is the thing that got him this notorious prize. And he kind of like was able to frame and kind of put all of these elements together into a cohesive package. So what I kind of told you is that like at the start of the 19th century, we thought that light was a wave. Maxwell worked really hard to show this. Hertz was able to generate them, and we had the Marconi kind of like propagate them across the Atlantic. And then these guys came along and they showed that actually light was a wave, but also was a particle. And actually we can now think and understand how kind of like, and now we use these tools to think, for example, of how we can treat a photon as an individual particle and play with its internal degrees. And that's something that Christian would kind of like tell us a little bit about. But interestingly, history doesn't repeat itself, but it rhymes. If you look back at Newton, he also thought that light was a particle. Turns out that he thought that, for example, diffraction and a lot of those effects were basically light interacting with the materials, and you could, if you kind of squinted at it, you could kind of get all the explanations. Then you couldn't get all the science, you couldn't explain all the phenomena, and that's why light became accepted that light was a wave. But what we're finding is that often the insights from different areas also come back to one another. And one thing we often see in science is that often you read a paper from 50 years ago, they actually had an insight that was either not appreciated or not fully understood. Okay, so I want to now tell you, so this is kind of fun. Yes.
So how do those equations work if they're not like correct?
They are correct. Then the way to think about it is that instead of when you think, for example, of a guitar string, you think that you can pluck it arbitrarily large, like as much as you want or as little as you want. What this is telling you is that there is like a smallest unit of energy that you can pluck with the guitar string. But the thing still behaves as a wave, but it comes in packets. So it's like you throw a stone into the water, but if it was such a small stone, instead of creating a ripple, it would just bounce off. You need to have enough of a stone that is big enough to kind of create a ripple, and then you have one ripple or two ripples or three ripples. Does that kind of give you a little bit of an intuition?
Sorry, I'm still a little confused. Because like if they only thought that light was a wave, I just don't get how like that would accurately predict.
So this connects a little, so maybe let me answer the question in a different way. So this connects to the point that Jose made at the start, which is like, on our day-to-day, we don't see this quantized nature. And the reason is that the number of photons that you get, for example, on this laser pointer is so big that we can't distinguish the individual steps. It's kind of like when you have like a 4K, when you go to IMAX and you don't see the pixels on the screen, that's kind of the intuition. It's like when our expectation from our length scale that we inhabit is so big that we don't see the pixelization that comes from like quantum mechanics. And we need to look at very faint phenomena. So in this case of the electron, it only works because we're able to translate the phenomena that happens one photon to one electron into a signal that you can measure macroscopically. So a lot of the science that we do to see this quantum mechanical effect is trying to isolate this phenomena where you can identify this one-to-one correspondence, or in the way that people are also pushing nowadays, actually building machines where we work really hard so that we can see one atom or one particle at a time.
So it's like the classical equations work on a larger scale and the quantum ones are like your particles?
Yes. You can imagine a different way of explaining is that also that if you think of these as kind of like number, the number that you get is like so big that the steps, the fluctuation or the steps are very small compared to the signal that you get. It's again trying to measure a dartboard over 1,000 miles. If you were off by half a meter, you'd be okay. So you won't be hard. It would be really hard to see that difference at the scale that we do. There's also a question over there.
I have two questions. So one of the equations was infinite, and then one of them was like it had a limit on it, and I'm confused like how that works because you said it's like a guitar string, like once you pluck it there's only a certain amount of energy that can go into it, so I don't understand how it could also be infinite too.
Yeah, so if you think of the guitar string, you can have arbitrarily like high frequency modes on the finite guitar string. But the key point is that when you have a particular temperature, you're trying to put some amount of energy on each frequency of the guitar string. But at some point, the plucking, even though it's 1 unit, it's much bigger than this quantity. So the guitar string just doesn't want to vibrate. And that kind of like cancels out the infinity of the number of modes that you have. Does that paint the picture?
I think so, like you can only put like it would be exponential, but you can only put so much energy into it, so then it's limited.
Yes, exactly. You said you had 2 questions.
Yeah, also you have the slide about a photon. I still don't really understand what it is though.
Yeah, so it's there's different pictures of how to think about it, but one way to think is that as light propagates, what you do is you kind of like create a pluck, like you try to pluck the electromagnetic field, and then it propagates. And it's like, much like in the case of the guitar string, you can only pluck in units, 1 unit at a time. And that eventually will propagate. It's harder to think because we don't have like the boundary conditions to think of modes in a very clean way, but the intuition is very much similar. Does that?
Wait, so it's
Yeah.
like, does, like, on that slide, I'm seeing like an electron, you see it, and then it moves over to the other side, and then it just stays there, like that's the photon, like,
Oh, sorry, the photon disappears. It gets basically absorbed. Sorry.
but like, what is it just light? Like, how is it different from, like, light?
Oh, it is what constitutes light. So maybe a different way, like when we think of classical, and probably the way that you heard the story of like electromagnetism is that you effectively have these equations, and you just need to understand the behavior of the electromagnetic field. But the way to think about it in this new language is that when you're trying to create a piece of light, you're actually generating many photons. So for example, you take a charge and you oscillate. What that is implicitly doing is it's generating photons, and generating, for example, a large number of photons. And then when they hit, for example, the board and they get absorbed by the material, you basically, what we call annihilate. You annihilate a bunch of photons, and they get absorbed and get transported into, for example, motion of the particles on the screen. So it's kind of, you can think of light as the generation, movement, and kind of absorption of these particles, these photons.
Okay,
Make some more sense?
yeah.
Perfect. I think you had a question.
I had one question. So I know when we were doing the equations, one was the issue was that it's infinite, right? If you apply more energy, it goes up and up and up.
Yeah.
But I don't understand why it's when we think of it in like discrete steps, that solves the issue of it being infinite. So is it after like a certain amount of steps, like in energy is no longer
Yes.
produced, or it's much less, it decays over time?
So let me see if I can draw this. So no, that's not what I wanted to do. Okay. So maybe explain this a little bit better. So one way to think of like this is an energy, and so is kVt, right? So imagine that you're at some energy that says that you're about here in terms of energy. So that tells you that for this particular mode of light, you're populating basically, on average, you have about 3 photons. And sometimes you have 2, sometimes you have 4, right? And if you have like a classical wave, you basically behave about the same. The amplitude kind of captures the same physics. But now as you increase the frequency, what's going to happen is that the spacing is going to get higher. So what's going to do is effectively your temperature is now below this point. So the number of photons here, you still can have energy in the system because it just sees this continuous spectrum. But now you're below all the levels. So you can't really have photons to contribute to that element.
That makes sense.
And that kind of like makes sure that that mode doesn't contribute anymore. Awesome. Great questions. Any other? Awesome. So I think I'm running a little bit long, but I wanted to kind of like, sorry. I want to kind of connect this to also the way that we now understand and manipulate light. So, so we kind of like, so far I've been discussing what happens when you have a hot object, which I used the stars. It's also fitting because we're in the Center for Astrophysics. But actually, if you think of the old-timey light bulbs, the incandescent light bulbs, they actually behave the same way. The way they work is by making something really hot, and then based on their spectrum, you have a little bit of visible light. Turns out that for those light bulbs, most of it is in the infrared, and that's why they're actually very efficient heaters rather than light sources. And here what you should think is that light comes off in all colors, in all manner. But more recently, we actually saw like these kind of ideas of like thinking of the quantum of light actually give us different kinds of lights that we can play with. One is you're probably familiar, which is the LED, which you can basically get in different colors. And this is fundamentally different from an incandescent light source because basically the intensity of light is peaked around one particular value. But there's another case, which is the laser, which is what I'm pointing out here. And it turns out that you can get lasers in different colors. But much like the same, you have a kind of light that only has intensity of one particular color. So what I want to kind of maybe spend the next 5 minutes kind of telling you a little bit is about the difference between these two, and how one side is monochromatic, but it's kind of incoherent, whereas the other case is what we call coherent. So all the photons kind of like behave in pairs. So it turns out that we still have a little bit of Nobel corner. The laser led to kind of like the Nobel in 1964. The ability to generate light in this coherent manner was kind of like a big deal. And it actually started in the context of microwaves. But it turns out that the LED was also a Nobel, but it's actually a much more recent Nobel. And it's also a Nobel only attributed to blue light. Turns out that for reasons having to do with material science, it's much harder to generate blue than all the other colors. And this was only recognized in 2014. And the fact that we have access to blue is why we now have access to like white light, white LED light. Because if you only had red and green, that would be a very annoying light to put in your bedroom. So how do these different sources work? The LED works with like this idea of a semiconductor. So I'll not go into detail, so I kind of just paint a broad picture. But the way to think about it is that you have two materials that are similar yet different in the following way. On the one side, you have a material that has a little bit too many electrons. This is what is known as an N-type, because it's more negative particles. And then the other is called P-type, which has holes. Or you can think of it of lack of electrons. So there's some electrons missing on the left side. And in general, these materials are happy to just coexist with one another. And you can actually look at the energy levels as a function of like the position of this material, and you get a step-like curve like this. But the crucial thing that people notice is what happens when you apply a voltage to these materials, is that you can actually move the holes in one direction and move the electrons in the other direction. And now there's a point in space where an electron is all the way super energetic over here, and there's a place it could live downstairs in this hole. So what naturally happens in these materials is that the electron effectively comes down and emits a photon. That's the only way that energy can go to. And this is the way that basically LEDs work. There's a lot more science on these semiconductors, but hopefully it's kind of, oh, I got it.
Okay, so a photon can cause an electron to move,
Yes.
but an electron moving can also cause the creation of a photon?
Exactly.
Okay.
Exactly.
Okay, yeah.
So if an electron's like a elementary particle, then how does it create a photon?
The same way that you have a charge, like the motion of the charge is the thing that allows you to create light. So you can think that the motion of the electron is the thing that allows you to create photons.
And is it like a photon? Wait.
So,
like, is a photon also, because if it's also considered a particle, but like an electron is not made of anything else,
so a photon, so that's a very good question. And that's like the entirety of like the Large Hadron Collider uses this idea, which is like from that perspective, you can just create photons and destroy photons willy-nilly. Why can I create and destroy electrons willy-nilly, right? Which is your question, like electrons, they should always be there, right? But photons, you're just creating and destroying them. Is that why are they different if they're both fundamental particles? Is that kind of a synthesis of your question?
well, I more just meant like I don't understand how a new particle can be created from an elementary particle. That like, because like where do you get the thing that makes the photon from the electron if it's just an electron?
The key intuition is going back to the guitar string, which is you should think of particles as excitations. So a photon is basically an excitation. So you have this electromagnetic field, and you just put some energy into the field. And you can create particles if you put enough energy.
I think it would be useful to like make sure we're defining particle, that a photon is massless, right? So you're not creating mass from energy being transferred. You're creating like a bundle of energy that behaves like there's mass behind it. So like when we're saying a a photon is created, we're using the word particle, I don't want you to think that like the particle therefore has mass like an electron. It's instead that like energy is coming out of an interaction of things, that there's extra energy that's available that is sort of bundled and shipped off together. That's how I can, and please like correct me if I'm doing a poor job of explaining it, but I think that might help to get where you are, is that like there's no,
Like it's not a thing.
it's not, it is, and that's, it's absolutely 100% a thing, because if it wasn't a thing, nothing would, you wouldn't, it's like, we can't say that it's not a thing, but it's not a thing, it's a thing, but it's not a thing.
So it like behaves like a particle, but it doesn't have some of the properties because
It doesn't have mass.
it doesn't have mass.
But maybe let me take that and take it a step further, which is like, the point that you make is really good, which is like, we initially at the 19th century thought of a particle as like a sphere that was just there, and it just was there or not. What this is telling us is that we should think of a particle as like a unit of something. And now what I told you is that light comes in these units, and that's why I call it a particle. Electrons are also units. And in principle, it's really hard to create electrons. And that's why in Europe they had to build a 27-kilometer tube and cool it down to 4 Kelvin, and put particles rotating at 99% of the speed of light, so they could smash them and put so much energy into it that suddenly new things can be created. So what I want to say is, like, as your teacher highlighted, the fact that the particle is massless, it means that it's very easy to create them. It's very cheap to create them. The electron has mass, so you need to put a lot of energy to create an electron out of nowhere. And that's why you don't see it in real life, and you actually need to go work, like spend billions of dollars to make it work. And Europe is planning to do it again.
I guess one way to sort of say is that the amount of energy in the universe is conserved, right? So we call it conservation of energy. But the number of photons in the universe is not conserved. We can destroy and we can create them and everything. But the amount of energy which is in the photons is converted into something else. So this is a sort of a broad brush picture of how we think of photons.
And there are rules for which particles you can create. Turns out photons are very easy to create, and that's why we get all this machinery to create light. Creating electrons is very hard. It comes in pairs with anti-electrons, positrons, and so it's very challenging to do that. And that's why we don't experience it in day-to-day life. Does that kind of paint a broader landscape?
So it might help, I don't know if we have time, but like to explain why, from like a chemistry perspective, why the electron is being, where that photon is really coming from, because I think that's part of what they're struggling with.
Oh,
It's like,
okay.
where is that energy, how does the electron now have more or less energy, and where, like, is that energy being created? So I don't know if you can touch very quickly on the chemistry of what's happening to explain what, like you say, there's extra electrons, but you're not just going to have electrons floating around, right? You can't just like take up a package. So I think that might help with some of the confusion.
So I don't know enough of the chemistry, but
We can be really basic, right?
yeah. So the intuition that you should have here is that you have a material that actually, the way that you get these extra ion particles is that this is usually silicon. I'm going to mess this up, but phosphorus is 1 to the right. So it means that on the lattice, the phosphorus has 1 extra electron. And so that one is okay navigating around the silicon. And on the p-time, you actually put a little bit on your silicon matrix. You put a little bit of the one on the left, which I'm blanking on.
Boron, I think.
Boron, someone said?
Is it?
Probably. I'll trust you on that one. And what that does is, like, suddenly there's 1 less electron than one silicon usually wants. And so for within the silicon matrix, it feels like there's 1 less electron, and that's what I'm calling a hole. And what is happening is basically as I change this voltage, what is happening is that an electron that used to be like floating on this background now finds a very cushy place that it can land on. And that's kind of how the energy goes from like being high to being low. And the extra energy, the only way that the system can go is like emitted into light. You should think of that, the electron effectively moving very rapidly. And that is what, much like the motion of a charge generates light, the motion of the electron generates light in this particular system.
In AP Chem, did you guys cover, I'm assuming you all took AP Chem, did you cover binding energy
Yeah.
in AP Chem? So it's getting to that like, that there is a, and this is part of the quantization, right? That there is a binding energy that occurs and when you put energy into the system the right way and you get the electrons released and there's all this energy that's then freed up in the system and it has one way that it can then come out of the system is as a packet of energy that's now massless, right? Which is why I'm calling it an excited electron, which is a question of Pradian. No, it's not. Look, this isn't obvious, right? This is the problem with ENM. This is not obvious, right? I couldn't. Yeah, please.
No, I think Ruben, I think in Ruben's lecture
We'll get a
is
little
where
more.
we describe spontaneous emission.
Fantastic. I'm sorry
So,
to jump
which
ahead.
is-
Oh, no,
Which is what is on the left.
Yep.
On the right, it is not spontaneous, and I think that's what Francisco is going to tell.
Yeah, and so maybe connecting, so the key idea is indeed that like there's a notion of a binding energy within the solid, and you effectively can decay and emit light as you undergo this process. The key point is that each of these like recombinations are kind of like random. So the light that you get out is completely like random by itself, and that's why you have incoherent light, but it's all at the same energy because the energy itself is determined by this difference, the binding energy in this case. The laser is actually quite different in that instead of having independent electrons, what you effectively put them is on a line. It gets a little bit more subtle than this, but this is kind of a good cartoon picture. What happens is that it's light amplification by stimulated emission. So what happens is that one electron effectively decays. You kind of work a little bit hard to prepare them all in the excited state. And then one of them decays. And what happens is that this photon then looks at this electron and stimulates the decay. And now two photons pop up. And this goes to the next one, and it goes more and more and more. And what you end up is a lot of photons, but they're all in tandem with one another. They're kind of like organized like an arbitrary.
Okay, so you said that the photon stimulates the other decay.
Yeah.
How does it do that without like losing energy or without?
Yes, so that's something that I think Oriana will touch upon. So there's kind of like, the nature of the photon is a special type of particle called the boson, and they like to come in pairs. They like to come together, and that helps the next one see that there's a photon there and kind of like induces it to decay faster. And so in this light source, you still have the same color, but you have like everything is in tandem and behaving together. And so you can actually check these differences, and that was like the demo that I had planned. And if you think of kind of incoherent light, if it's all incoherent, you never have like any interesting pattern. You take two pieces of incoherent light together, and the only thing that you get is that intensity increases. But if you now have this super coherent light, it behaves as a wave, right? So if the phase is the same between the two sides, you get amplification. And if they're somehow out of phase, what's going to happen is that they're going to cancel out. So in principle, if you do kind of an interferometry experiment where you try to do these kinds of experiments, you can actually see the difference between the incoherent light and the coherent light. And that is what I want to kind of highlight using these two-slit experiments very closely, which is like if you have incoherent light that just behaves like independent particles, when you try to shine it through an object, you just see the shadow on the other side. But if you indeed have a wave, what's going to happen is that as light goes from one slit versus the other, you should actually see an interference pattern on the other side. And you should see a pattern like this. And now, the hope is that you can effectively see this. So let's see if we can make this work. So, for example, this is what happens when you shine a laser through a single slit. And you can see over there that it's not just one dot. It has all of these peaks on the sides.
If you need to stand up and move closer to the screen, like, to be able to see, is
During
that
the
all right?
break, you would be able to do it yourself too. Okay?
Yeah,
So-
okay. Oh, good.
Yeah.
Is nothing able if it's like farther from the screen?
It might just diffuse.
Oh.
But it's
Can you
how
see
the
it
laser-
or?
Yeah, I see that.
Yeah.
So this is a little bit
Oh.
easier. So you see that I'm passing it through two slits, and suddenly the light generates those fringes. So it's not just a blob, right? And if I change like the size between the slits, I get different patterns because the interference itself is going to be different. And you can kind of see that if you change the frequency of light, you get the same effect, but the interference pattern itself is slightly different. By contrast, if you take like an incoherent light, so this is just red, and you try to aim it, you just see a shadow. And even if you try to zoom in, you don't see basically, well, the light is not the most collimated, but you basically only see a shadow. You might see a little bit of fringes, but you don't see the level of like interference pattern that you get exactly when you have all the photons working in tandem. And now, so people can play with that on a little bit on the break. That's way too bright. That's somehow, oh, perfect, thank you. Okay, so I wanted to end with not just telling you that like everything is done. So if you just search for laser on Nobels, you actually get that already 5 of them directly use lasers as kind of like the key insight that went. If you think a little bit more carefully, it turns out that 4 more you can directly attribute to the availability of lasers as a tool. So the laser has gone from something that we kind of like work really hard to build to something that we use nowadays every day for the most interesting things like detecting gravitational waves or just pointing at things. And indeed, if you go on Wikipedia, you can look for laser applications of laser, and probably the most meaningful is the development of the PlayStation. But also, like when we think of like medical device like LASIK and kind of like a bunch of other things, we use like the fact that we have access to these like light sources actually driving the kinds of technologies that we can build. You can also get cool light shows in laser cutting, but we're not done. As I kind of emphasized, like having access to lasers is kind of cool, but it turns out that building lasers of different colors is really hard, especially as we move to different colors. So this is something that people still think about. One thing that people care a lot is actually building kind of like better, faster, and stronger lasers, and even smaller. So this is kind of like, this feels like a weird thing. Why is this a laser? It turns out that this is like the cavity that you need to kind of bounce light to create the most accurate laser that I think we have, right, Ruben? Like June said. Yeah. So this is like, you need this to basically, it's like a block of silicon, of like isotopically pure silicon that you need to basically build the best laser. And that has allowed us to build the best clock. But also, I kind of emphasize the laser as a kind of quantum source of light. But now that we have access to the, like, thinking of the photon as an individual particle, what people are excited is like thinking of like different kinds of correlations between photons, and even thinking of different kinds of like quantum states of light. And this is necessary as we try to do more and more precision measurements. And also, like, as we think of like at the quantum level, it's kind of like allowing us to do new things. For example, these kind of ideas of quantum computation that I think Christian will talk a little bit about. And I think I'm already over, but I want to thank you all for the very nice questions, and hopefully that was cool.
I think in the interest of time, and also during the